this water is basically coming out of this subsurface flow. So what you are seeing, this water, small trickling water here, is nothing but a small spring which is flowing and which is normally tapped by the local communities for their local water supply. And this is what we are trying to look from the water disaster towards the scarcity side, how the local communities are being affected. So when we talk about the springs in Himalayas, we do talk about the millions of springs. We do not have an inventarization right now, how many springs are there, but a broad number have been talked about millions of springs, which are not only the local, the lifeline of the local community, but also the starting point of the headwater catchment streams. So they are drying off. The local community are dependent on that. And when this water is moving into the soil profiles, we do not really have a more clear-cut science understanding. How does these springs are working? What are the different typologies? How these systems are behaving under different land use, land cover? So there is a policy issues. There is a huge socio-hydrology or socio-economic issues. How do we handle the local community handle? So we need to have the situational assessments of those local systems. We are also bringing the science into it. How does this, the hydrological, what is the quantification of these springs under different regimes, and especially in the lean season, when there is no rain, then that is the time where the local communities are more dependent. How can we translate that into the policy side? So those are the major water scarcity questions we are asking in our research. So this is what we do in our instrumentation. So we do have we put the flumes, different typologies of the spring. So this is a spring which is going to flow out, where we put the spring, the flume, and a water level recorder to measure the water level in the springs at different locations for to measure how much the discharge is happening. We did not stop there. We basically also started instrumenting the automatic weather stations to capture what is the hydrometeorological parameters which are changing over the time at different locations. And then after understanding the characteristic of the springs under different rainfall regimes, we also went into another area from last 1.5 years, working on the isotopes. So how does the natural isotopes are going to tell us more information about the water which is entering from the rain into the soil profile and into the aquifer, and then sprouting out at the spring outlet. Along with that, as Jürgen just mentioned about, my interest is also into the instrumentation. So this is a sampler which we normally got from the isotope sampler, which is a pretty expensive sampler from other part of the world. We have designed our own indigenous based water sampler here, and we have been testing that. So that is another area where a lot of science and a lot of interest lies there to answer that. So the major questions we are asking in the spring hydrology concept is, how are the different spring flows can be characterized under different typologies? Can we also see how the weathers are changing? How does it impact the rainfall patterns on the discharge? And then finally, what are the different aquifer in terms of the isotope? What are those isotope analysis can tell us how the water is moving into our aquifer system? Just to give you a brief idea, so the first part, when we do instrumentation just for the hydrology component, how does a spring will behave under different rainfall pattern? So we have on the top, what you see here is one of the spring site, which is in Almora, Uttarakhand state. And we have rainfall on the top bar, and then we have a spring discharge, which is in liter per minute, which is a small spring, not very big springs. Like in Italy, we find a lot of big springs. So the spring discharges are behaving, are basically reflect how does the rainfall is moving into aquifer system. The similar site, we have another site which has 3 springs at the same hill slope, and where we find that how does this springs are behaving. These springs are at the same location at different altitude, same rainfall happening, but the behavior are different. So the first top spring is the spring which is on the top, but it is yielding more water, yielding more discharge. But at the lower part, they are not. And then sometimes they are also not really reflecting the impact of the rainfall. So what does basically, this is what we are trying to answer here is, do we have the same aquifer, or there are multiple aquifers which are feeding into one aquifer system, one spring system? And that is the type of data we need to collect to understand. And it is important. The reason is because when we do take that data and then put them into a recession curve part, we saw that there is a drastic change in between two springs. So there could be a spring which will have a lot of water to absorb and hold and release it very slowly. But there could be a spring which can be a different geological setup, which can drain out very fast. So that the methodology, the interventions to conserve that water from the rain into the system, we have to have a different methodologies and different interventions needs to be implemented. As of right now, there are a lot of interventions being done in the Himalayan spring systems, but they are at a blanket level. So that is what we are trying to capture, those data, the variability, and then the behavior of those springs. When we move on to the second part of these studies, we also started using the isotope just to understand where is that water coming in. What you see on this graph is the on the x-axis is the O18 isotope, and then O deuterium on the y-axis. And when we develop the local meteoric water line, we try to see, okay, where are those spring signatures are lying down on the isotope side. Using that and the hydrochemistry of the spring and the stream and the rainfall, we are trying to find out where are those entry point into a spring system. So this is the same watershed where we have multiple springs which we are monitoring on this, mainly on these aspects a lot. So it's a little heavy slide, but I just take you 1 minute there. So if you just see and focus on this, one of the spring here at C as top, what you're seeing here is the spring outlet here. And based on the isotope and the local meteoric line, what we are saying there is, so this location of the spring is at the level of 1766 meters above mean sea level. And based on those elevation and the deuterium and the oxygenating signatures, what we are estimating is the water entering is at the level of around 2,297 feet in that, or 700 meter above that location of this spring system. That means the water which has fallen in this region has basically infiltrated and then is coming out from this. Why we did that? And we did it for almost like around 10 springs, just to find out where are those locations in the catchment where the water is coming into the system and coming out from the spring side. The idea was to, based on the hydrogeological mapping, we can also identify the recharge area. And what we are cautioning here is in this project is, do we have a good understanding through hydrological maps? Can we identify those recharge areas? We do not have to do the isotope analysis for all the springs because it is a lot of work and needs to be done in that. So that is the main caution, and we are still working on that. We do have a good convincible number data sets, but we are still working on that. The second part of our water pathways are when the water moves into the different ecosystem, be it also the grasslands in the Himalayas or the different ecosystem, as I mentioned about pine or oak systems. The water can take a different pathway based on the soils and the forest, on the soil properties and on the topography. But that has an information to tell about the forest policy. That is what we are trying to focus there. How do that understanding of the water moving into different ecosystems can help the forest policy to be changed, to be revisited. And the same side, but also the water moves in an urban system, which is a city which you are seeing on the bottom right side, is the Bindal Rao. It's a small stream in Dehradun, very close to our city in Roorkee. And it is a stream which is basically an urban stream, but gets flooded quite a bit of time in a monsoon season. And the people get affected, of the local community, especially the vulnerable community which are living very close to this stream, and they get affected by this. So how does that system, and how do we can answer that? So moving on to the first part of the land use impact. So we did a lot. We did studies on the hill slope scale as well as the plot scale under different ecosystems. So one first part we did it a long time back on a hill slope where we instrumented the hill slope of two different ecosystem with grasslands and a degraded system to understand what type of runoff generation mechanisms are occurring under different rainfall pattern regimes and how does they are connected in terms of the soil conductivity, how the runoff generation areas can connect it to the outlet. But the other question which recently we are also answering is how does the water is partitioning under different ecosystem? And there is still a caution and a demystification needs to be done about what is good. Is oak good for an ecosystem or is the pine good for the ecosystem in terms of the hydrology or the hydrological response? So in that way, basically we have instrumented at a plot scale as well as the watershed scale. So on the right, what we are seeing a big plume here, it is the outlet of a pine watershed, which is a headwater catchment. But on the left side, what you see is the plot scale studies which we are doing. So on the leftmost side, we have a plot of 3 meter by 1.5 meter wide. At the end, we have a flume with a rainwater level recorder, so that when a runoff going to occur from a plot, it is recorded. We do have a moisture sensors at different locations in the soil profile. What are these? These are nothing but we did try a lysimeter, a zero tension lysimeter under the plot so that some leaches can be collected. Every field instrumentation never works with my experience. So we were not very successful in getting the leakage under this plot. So we need to improvise it. We need to see where we went wrong. But the rainfall plots really worked out well, and we are analyzing that. The third panel, what we're seeing here is under the pine, we have the collars which to capture the stem flows, but also the through fall systems under the canopy. So just to measure the through fall and the stem flow under under the pine system and under the oak system. And this is at the right, bottom right is the sealing well for the outlet of the oak watershed. So what we are trying to understand is how this partitioning is happening in a particular canopy. When a rain occurs, what is the through fall happening, what is the stem flow happening, and how much the canopy intersections are happening. So this is the way we set up the pine and the oak system. And what you're seeing here is the yield outlet coming out from the pine and oak watershed. So the rainfall patterns are very similar because they are very close by. These are pine. This is on the pine side, pine watershed, and the oak watershed. What you are seeing here is the mass curve of the rainfall mass curve, which is reasonably fine, like in terms of the rain mainly measured. This is 1 year data set for the last 2022, and which we have a higher, mainly the rainfall happening in the monsoon season. And the pine has a very small water yield happening as compared to the oak side. When you see the dotted line is the runoff mass curve, where we have reasonably good yield coming out. So what it also shows that the forests are holding a more of water and yielding it very slowly out of the system. But still a lot of information. It depends not only on the forest type, but also the soil and the canopy and the how does it let the water infiltrate into the soil profile. What you're seeing here on this panel is very interesting data. It is very recent data being analyzed. So what you're seeing, the circle is the pine and the squares are the oak. On the y-axis, it is the through fall percent and the total precipitation on the x-axis. What you're seeing on the circles are very clear of the pine that there is as the rainfalls are increasing, there is an increase in the through fall percentage. But we still are understanding and sketching the data. Under the oak system, as the rainfall is increasing, the through fall is reducing here. In both the cases, under the stem flow percentage conversion of stem flow percent on the y-axis, on the total precipitation on the x-axis, there is the stem flow is increasing with the total amount of precipitation, and in both the cases, it is less than 1% of the total precipitation. The through falls are of the order of 66 to 70% in both the cases. There is a slight difference in the pine and oak. So what, in an indirect way, we are saying that there is a huge amount of intersection losses happening on the canopy, which we are still trying to get those numbers closely. The reason there might be some error in the interception losses is because we are collecting these drums and the water at a weekly or a cumulative way, because we cannot send a person, it's not automated. So the person goes after 4 event or 3 event, and that's the total amount of water which has been collected in these drums, and that converted into the percentage of stem flow or the through flow. For that, what we are now working on, and we almost done, we are going to install this. So what you're seeing on the left bottom panel is a tipping bucket, in-house tipping bucket, which is of the order of 200 to 300 ml at one bucket to fill it, and so that this tipping bucket will be installed at this outlet where we can collect the water or the stem flow and through fall as the rainfall is happening. So we can correct which time of the rainfall event the rate was high or low, and that is what we are trying to improvise the data in this time frame. So the second part of the same land use and the rainfall happening in the Himalayan system is in a urban system, is mountainous systems are really getting affected by the flash floods, the variability, the spatial and temporal variability of the rainfall in this mountainous catchment. So the complex system is complex. It's topographically and the variability in the precipitation happening in that. We do have a less infrastructure because these communities and these hydrological catchments are small. So there is not a lot of data or the instrumentation which you get from that system, and still they are facing a lot of major issues in the flash flood, and communities needs to be warned, and that is what this work we have worked. So this work is being done under a UK COP26 UK NERC project, where this is the catchment, a small catchment of 44 square kilometer, which is very close to our city Roorkee in Dehradun. What we are seeing here is the low-cost sensors. The water level sensor is the LiDAR-based water level sensor, which has been installed at different locations on the same stream, starting from the top to the bottom. So we have 3 water level sensors, top and middle and the lower part. And then we have 4 rain gauges over the catchment. It's a small catchment, but we try to see, okay, how it is happening, which communities are getting more, which are more vulnerable to those areas where we have flooding happening. And again, this is the communities which are very, very close to this location, which are basically sitting onto the banks of those. And every time though they get flooded or they get damage of their houses. Again, a snapshot of the data set. This is what the left panel of the top is basically the September 2022, last year September data set. 3 rain gauges. Every time, not all the instrumentation works. Sometimes something happens and it will not work. September 2022, what you see here is a blue bar, which is again a cumulative rainfall. It's a rainfall mass curve. Within this 1 month, within that small catchment, there is a difference of 187 mm rainfall within the small catchment. So there is a huge spatial variability happening within that small catchment or hilly catchment. And that is also seen in this year's data non-monsoon season from January to June 2023, which is sort of a non-monsoon season when it doesn't really rain. Within that non-monsoon season also, we captured around 220 mm of difference within that catchment. Within the monsoon season, like in September last year, also got a good number difference. And when we divided that events into a different event base, so what we are seeing here is the RG1 peak intensity is the top rain gauge, RG2 is little lower elevation, RG3 more lower middle, and then RG4 is the lower part. So what you're seeing here is during the monsoon season, the higher intensities are normally at the lower part of the catchment. So the intensity is what you are seeing here in the lower part is reaching up to the 90 mm per hour intensity, or little middle part around 100. So they are clustering around, very clearly they are clustering around that during monsoon, the system is on the lower side and they are dissipating or they are pouring down in the lower part of the catchment. But during the non-monsoon time, the upper reaches are basically getting more rainfall and higher intensities. So it's very, very clear that there is a huge temporal and spatial variability happening in this catchment. And not only that, there is a clear picture of the intraday variation happening within this system. So the system is complex. So basically, what you're seeing here on the bottom panel is the major rainfall in this small catchment is normally starts in the evening part and it goes up to the late night, and some events normally in the middle part of the day. But major rainfall is happening, and that is a very crucial time when the people are sleeping and the what rain starts happening in the night. You really do not know what is really happening in the stream, and that is where the warning system comes into picture. So what we have is the response time of those catchments. So basically, what we are seeing here is the main 50%, more than 50% is the catchment is urbanized, and it is really generating a high surface runoff. This is the water level at two locations, and with the stream, and the hydrological response of two sites where we really got good data set to be collected is like around 50 to 30 minutes only time where the water starts increasing in the stream, which basically causes the flood. We did not stop there. So again, this work was a part of the UK and partners from University of Birmingham, Imperial College, and the local NGO from Dehradun, People Sen Institute. We started developing a smart concept where we shared the understanding. So we start with the talking with the people. Okay, how can we make a community-based early warning system for flood using the low-cost sensors? So where we had a stakeholders meeting from starting, where so that we decide which are the locations to be put as a sensor to monitor. So we monitor the system, and then they start getting the data, and then idea is to basically disseminate that. So we are in the process of to eventually build up this early warning system to disseminate to the local community. I'll go on to the third part. As we are in the Himalayas, so we do have a lot of high gradient rivers is happening. In this, one of the catchment which I have been monitoring from in my 10-year or 12-year experience in India and in IIT Roorkee, I have a river catchment which is a Aglar River watershed, which I have been monitoring from last 10 years. In this, a sub catchment is Palighat of 60 square kilometer, and the upper Aglar part is around 100 square kilometer. Here in this system, what you are seeing is a very typical Western Himalayan system, and you have a lot of debris or a lot of bed load material moves into the system. Though they look small, but the amount of the bed load material which is happening in this system is huge. So we asked the question that what is the best way of what is the contribution of the partial and the full transport conditions in the overall bed load material transported in an annual or a monsoon season? What is the best way to basically estimate that? Because what in the literature we do not really have, or we do not have a good estimation observed data for the bed load material. It is a tough job. It's not that easy. So we are trying to develop, and we did develop a virtual velocity method, applied a virtual velocity method to get the bed load transport happening in this type of terrain rivers. What we did is the painted tracer method. So we painted the sediments and the gravels on the riverbed at different locations, and we saw after the different events how much the the sediments have been moving out of those systems. So using the virtual velocity method, in which we basically calculate the mass fraction transport for the ith size of the gravel, the sediment, and then we eventually calculate the total transport into the system. What we found out here is, so what you're seeing here on the left panel is the bed material transported. The dotted lines are mainly the Aglar, the measured data, the partial movement and the full movement. So partial is the lower envelope, and the upper envelope is the full transport. When we applied the other sort of conventional methods which have been applied at universally accepted very well, these numbers are not really great and applicable in our data. The numbers are way off. So we are basically developing our own methodology to at least get these numbers closer. We also check is our system, because if you see here, there is a jump between the partial transport to the full transport. So that is where, again, the research and our student, we are working on how do we answer this, how do this jump is happening from the partial to the full movement, and what is the mechanism which is happening there. And we do also find out is a active layer depth is playing a role there in the jump of the from the partial to the full transport. So we did again apply the different methods in the literature, which we are able to find out they are still not working well to really give the answer in the active layer depth, which we again developed our own equation to incorporate the different factors for the jump in their system. The bed load transport estimated from a virtual method is around 67,000 tons. It's not a small amount of material which moves, which we do not have the numbers, but that is the estimates which we estimated from our field study. And for the polycard is around 18,000. So the numbers are very, very high. And out of this, around 60% is normally the monsoon transported, but still the overall, the non-monsoon still has a lot of big numbers. We still trying to develop the formulations for the active layer results towards the better estimation. So still we are characterizing the active layer depth, how it is being affected, can affect the bed load transport. So what we move on to the pretty much the last topic of my talk is the Himalayan lakes. So what you're seeing on this buoy is one of the first. I'm really happy to also. I'm pretty proud of my research group that this is a lake. This is a lake buoy which has been right now running for last 1 year, which has the water quality sensors at the 4 meter depth, and it is running. It's a real-time online system in the Lake Nainital, where again this lake is surrounded by the whole huge hill city, dependent on this water body for the water supply for the whole city, as well as the tourism in the summer part. What we did is last year, from last 2021, the first visit starts. Basically, we 2022 we covered the whole data set, so almost 2 years data set. So we are collecting the weekly water quality profile. That is a manual. We do it from the inlet to the outlet part. We also have a automatic weather station to see how the hydrometeorological parameters are changing. And the buoy is collecting every minute data set just to check the sensors, and the data is coming good, and though the accuracy is not that much. Why we started doing that? The two questions we were asking there, because this lake is not really majorly governed by the surface runoff inflow. It has a huge catchment behind where we have another small lake, which we call Sukhatal Lake, which is supposed to be the recharging area of this lake. It's mainly the subsurface dominant fed lake system. And because of the urbanization, so that system is getting affected. So what we started doing is we started measuring the inflow plus also the water quality side. In the past literature, we have also seen that the lake has been defined as a lake stratification happens for 8 months. But when we started looking for the data for our collected data, what we are seeing here is a very, very less mixing of the lake or the stratification of the temperature happening in the. So these are the monthly data for 2022. So this is aggregated of weekly data together and at different depths on the y-axis. So what you're seeing here is some variation. Basically, the whole system is mainly mixed as temperature. There is no stratification happening within the depth profile, but some changes are normally happens is in the later part of our spring system, basically thermally mixed from November to February part. That is the part where we have some thermal stratification happening in that. Similar things are happening in the DO part. So what we have also been collecting is the SATIDISC data set for the lake for weekly. And when we plotted that, SATIDISC data set is nothing but the transparency data to see how deep the water is transparent. So based on that and a simple trophic state index equation, when we put it together, we can do it for the water quality, including the water quality parameters. We have not done that. But majorly based on the SATIDISC, the major part of the year of the temporarily the lake is into the eutrophic side, but some part is more onto the mesotrophic condition. So what I have broadly covered here is the 4 aspects of water in the Himalayan system, moving from the aquifer in the different ecosystem, high gradient river, when we have a lot of bed loads moving into the system, and how does this lakes in the Himalayan lakes are happening. What we can conclude here is There are different typologies which are playing a big role in the springs as a mountain aquifer to behave under different conditions and how they are drying off, because these are important for the local water supply. The huge monitoring of the bedrock material moves into the different catchments under the natural conditions. So the systems which we measured for the bed load are natural. They are not affected by any regulation, any anthropogenic activities happening much. It's a pretty pristine, unregulated system. And still the numbers are very high, but still the monitoring techniques needs to be more improvised, more monitoring needs to be done to get the clear data. Also, the pine and oak forest has a very clear-cut budget, what hydrological budget differences, but still a lot of data needs to be collected for the pine and different ecosystems. We were able to really do a good job in using the low-cost sensors to develop the community-based flood early warning system. We are in the designing part. We conceptualized it. Theoretically, we have designed it. It's just the lake that we will be implementing it soon. And in the lake Himalayan system, the clear cut, there is a huge effect on the lake, on the anthropogenic activities happening onto the lake system of the Himalayan system. But I am still sort of a proposer of huge long-term hydrological monitoring sites are still needed in the Himalayan system to be monitored under different hydrological systems. So every time I say that, I'm looking forward for more collaboration. These systems are complex and cannot be monitored by a single research group. It needs a lot of hand holding and to a lot of collaboration to take it forward, to answer a lot of big questions. Yeah, with this, thank you very much. Thanks for your time and thanks to you.